Hello, hope you guys can hear me. Going to be doing another calculus stream. I think this one may be smaller, like it would be a 1 hour stream. Or if I'm in the mood, I might do it longer. Let me change to full screen. So last time I did, what did I do? I did partial fractions, other strategies of integration. What was numerical integration? And also I did improper integrals, where it's going to infinity. Oh, I remember. Where we break it up into discrete parts. Use the trapezium rule or Simpson's rule. Okay, let's try this now. Introduction to differential equations. Basics of differential equations. If this opens, that is. Consider the equation derivative of y is 3x squared, which is an example of a differential equation because it includes a derivative. Let me read this first. Calculus is the mathematics of change, and the rate of change are expressed by derivatives. Thus, one of the most common ways to use calculus is to set up equations containing an unknown function y is equal to f of x and its derivative, known as a differential equation. Solving such equations also provide information about how quantities change and frequently provides insight into how and why the changes occur. Consider the equation derivative of y is equal to 3x squared, which is an example of a differential equation because it includes a derivative. There is a relationship between the variables x and y. Y is an unknown function of x. Furthermore, the left-hand side of the equation is the derivative of y. Therefore, we can interpret this equation as follows. Start with some function y is equal to f of x and take its derivative. The answer must be equal to 3x squared. What function has a derivative that is equal to 3x squared? One such function is y is equal to x cubed. I mean, it would be any form of x cubed plus c, right? Uh, Differential equation is an equation involving an unknown function y is equal to f of x and one or more of its derivatives. A solution to a differential equation is a function y is equal to f of x that satisfies the differential equation. So you're just doing integrals. But the unknown function might appear like this. Note that a solution to a differential equation is not necessarily unique, primarily because the derivative of a constant is zero. Okay, verifying solutions of differential equations. Verify that the function y is equal to, well, this function is a solution to the differential equation. Okay, never mind that. The order of a differential equation is the highest order of any derivative of the unknown function that appears in the equation. What is the order of each of the following differential equation? I guess over here it's 1, 3, 4. 1, 3, 4. The highest derivative. Guess over here it would be 5. General and particular solutions. We already noted that the differential equation derivative of y is equal to 2x has at least two solutions. The only difference between these two solutions is the last term, which is a constant. What if the last term is a different constant? Y is equal to x squared plus c is a general solution of the differential equation. A graph of some of these is given in figure 4.2. A particular solution can often be uniquely identified if we are given additional information about the problem. Find the particular solution to the differential equation passing through the point 2, 7. Let's try this. I like writing it like this. 2x y is equal to x squared plus c. We know 2, 7 is a point. So 7 plus c. C is 7 minus 4, 3. So y is equal to x squared plus 3. Initial value problem. Usually a given differential equation has an infinite number of solutions, so it is natural to ask which one we want to use. To choose one solution, more information is needed. Some specific information that can be useful is an initial value, which is an ordered pair that is used to find a particular solution. A differential equation together with one or more initial values is called an initial value problem. The general rule is that the number of initial values needed for an initial value problem is equal to the order of differential equation. Oh, I see. For example, if we have the differential equation, this, because what I think is, if we have something like dy by dx 3 times, I will write it the simple way. 2, 3 plus it with 1, 2. If we have something like this, there's a plus c for the first derivative, and then another plus constant for this derivative, and another plus constant for this derivative. So we need like 3 values, 3 points for each of them, I think. The general rule is that the number of initial values needed for an initial value problem is equal to the order of the differential equation. It wouldn't one initial value be enough? For example, if we have a differential equation, then y3 is equal to 7 is an initial value. When taken together, these equations form an initial value problem. The differential equation, this differential equation is second order, so we need two initial values with initial value problems of order greater than 1. Verifying a solution. I want I want a problem where I have to find the solution. The initial value problem consisted of two parts. In example 4.4, the first part was the differential equation. So let's see. So what are they doing here? Derivative of y is equal to 2y plus 3 e to the power of t. The derivative of y is minus 4 e to the power of minus 2t plus et, right? And then plus 2y is written over here. So simplifying, we get 3et, 3e to the power of t. The second part was the initial value, y0 is 3. These two equations together form the initial value problem. Three e to the power of x plus x square minus 4. Y0 is equal to 5. If wait derivative derivative of all this is equal to 3 e to the power of x plus it with x square and then minus 4. So I can write y like this. And y oops and y0 is equal to that means 5 is equal to 3 plus 0 minus 0 plus c, and then that means c is equal to 2. So the equation of y is 3 e to the power of x plus e cubed over 3 minus 4x plus 2. Okay, velocity of a moving baseball. A baseball is thrown upward from a height of 3 meters above Earth's surface with an initial velocity of 10 meters per second, and the only force acting on it is gravity. The ball has a mass of 0.15 kg. Find the velocity of the baseball at time t. So, thrown upwards 3 meters above the Earth's surface, then initial velocity of 10 meters per second. 10 meters per second. So force is equal to mass times acceleration. Acceleration is constant. Three meters. This is going down 10 meters per second. And 0.5 kg. 0.15 kg. The initial mass is 10 meters per second. The initial velocity is 10 uh, meters per second. The downward acceleration is minus g, but the initial velocity is 10 meters per second, right? It's minus g is 9.81, 9.8 meters per second squared. So then v is minus 9.8 plus c. Is that correct? If I derivate this, I get this. No, wait. If I derivate this, what am I doing? 9.8t plus c. So this is 0 plus c, and then c is 10. Find the velocity of the baseball at time t. So vt is minus 9.8t plus 10. What is the velocity after 2 seconds? That is 9 minus 9.8 times 2 plus 10. Why does the mass matter? Why does it matter if it's 3 meters above? A baseball is thrown upwards from a height of 3 meters above the Earth's surface with an initial velocity of 10 meters per second, and the only force acting on it is gravity. The ball has a mass of 0.15 kilograms. Find the position S of t of the baseball at time t. Uh, the ball is thrown upwards from a height of 3 meters. Ball up 10 meters per second. Um, and has a mass of 0.15 kg. So it's equal to Vt. S is from the uh, Earth's surface, right? Like when we say S, the initial height S0 is 3. And the derivative is plus 10. Oops. Derivative at 0. It's plus 10. Find the position of the baseball at time t. Like that. And the derivative of this would be equal to Vt. But does that make sense? Because I don't think Vt should be treated as a constant. No, I don't think this is right. t minus 9.8 plus 10. Now this makes sense. Just like that, if we derivate this, we get this. Hold on. For the previous question, was it going? It's thrown upwards from a height of. No, this is wrong. It's thrown upwards. Anyways, 0 is equal to 3. Uh, yeah. Um, yeah, then I got the equation right. Find the velocity after 2 seconds. So do this, and then simplify. Find the velocity after 2 seconds. Wait a minute. Isn't it the same as the previous question? No, I'm in the wrong thing. Find the height after 2 seconds. That's when you substitute. Yeah. Directional fields and numerical methods. This sounds tough. For the rest of this chapter, we will focus on various methods for solving differential equations and analyzing the behavior of the solution. In some cases, it is possible to predict properties of a solution to a differential equation without knowing the actual solution. We will also study numerical methods for solving differential equations, which can be programmed by various computer languages. Direction fields, also called slope fields, are useful for investigating first order differential equations. In particular, we consider the first order differential equation of the form derivative of y is f of two variables x and y. An applied example of this type of differential equation appears in Newton's law of cooling, which we will solve explicitly later in this chapter. First, though, let us create a direction field for the differential equation. Here T represents the temperature in degrees Fahrenheit of an object at time t, and the ambient temperature is 72 Fahrenheit. What are these arrows? The idea behind a direction field is the fact that the derivative of a function evaluated at a given point is the slope of the tangent line to the graph of that function at the same point. Other examples of differential equations for which we can create a direction field include this 3x plus 2y minus 4. To create a direction field, we start with the first equation. We let y x naught and y naught be an ordered pair, and we substitute these numbers into the right hand side of the differential equation. For example, if we choose x is equal to 1 and y is equal to 2, this y is inside the latex. Substituting into the right hand side of the differential equation yields, okay, derivative of y is 3. This tells us that if a solution to the differential equation passes through the point 1, 2, then the slope of the solution at that point must equal 3. To start creating the direction, uh, to start creating the direction field, we put a short line segment at the point 1, 2 having slope 3. I don't get these arrows. We can do this for any point in the domain of the function which consists of all ordered pairs in R squared. Therefore, any point in the Cartesian plane has a slope associated with it. Oh, I guess the arrows, they show the tangent line, the derivative, because the equation is defined for all the values. 3x plus 2y minus 4. No, the derivative is this. Uh, nope. Okay, so the actual line will depend on the whatever plus c is, the graph. I think I get it. All these arrows represent the derivative, this line. But from the derivative, we can't get the original line. So all these arrows represent the possible, all the derivatives at that point. And these two red lines, they're for a specific case where the initial temperature is 72 Fahrenheit. A direction field, slope field, is a mathematical object used to graphically represent solutions to a first order differential equation. At each point in a direction field, a line segment appears whose slope is equal to the slope of a solution to the differential equation passing through that point. Using direction fields, we can use a direction field to predict the behavior of solutions to a differential equation without knowing the actual solution. For example, the direction field in figure 4.7 serves as a guide to the behavior of solutions to the differential equations. Derivative of y is equal to 3x plus 2y minus 4. To use a direction field, we start by choosing any point in the field. The line segment at that point serves as a signpost telling us what direction to go from there. For example, if a solution to a differential equation passes through the point 0, 1, then the slope of the solution passing through that point is given by this minus 2. Now let x increase slightly. Let's say x is equal to 0.1. Using the method of linear approximation gives the formula for the approximate value of y. In particular, this, okay. At this point, the slope of the solution changes again according to the differential equation. We can keep progressing recalculating the slope of the solution as we take small steps to the right and watching the behavior of the solution. Figure 4.8 shows a graph of the solution passing through the point 0, 1 and all the derivatives. All the arrows represent the derivative. The curve of the graph uh, the curve is the graph of the solution to the initial value problem. Derivative of y is equal to 3x plus 2y minus 4, where y0 is equal to 1. The exact solution to this initial value problem is this. Y is equal to minus 3 over 2x plus 5 over 4 minus 1 over 4 e to the power of 2x. Now consider the direction field of the differential equation. Derivative of y is equal to x minus 3, then y square minus 4, shown in figure 4.9. This direction field has several interesting properties. First of all, at y is equal to negative 2 and y is equal to 2, horizontal dashes appear all the way across the graph. This is positive 2 and this is a negative 2. Therefore, y is equal to minus 2 is a solution to the differential equation. Because I guess y is equal to negative 2, then the derivative would be 0. By solution, they mean where the derivative is 0. Similarly, y is equal to 2 is a solution to the differential equation. These are the only constant values solutions to the differential equation. As we can see from the following argument, suppose y is equal to k is a constant solution to the differential equation, then y, the derivative of y is 0. Substituting this into the expression yields 0 is equal to x minus 3 k square minus 4. This equation must be true for all values of x. So the second factor must equal 0. This result yields k square minus 4 is equal to 0. The solutions to this equation are minus 2 and 2. These are called the equilibrium solutions to the differential equation. An equilibrium solution is any solution to the differential equation of the form y is equal to c, where c is a constant, because this will help us solve the thing. Yeah, so y is equal to -2, it's a constant, and the derivative is 0. Consider the differential equation. Derivative of y is equal to f of x and y. Assume that all solutions to this differential equation are defined for x is greater than or equal to x naught. Let y be k. Let y is equal to k be an equilibrium solution to the differential equation. Y is equal to k is an asymptotically stable solution to the differential equation if there exists epsilon more than 0 such that for any value uh, c, which is an element of k minus epsilon and k plus epsilon, the solution to the initial value problem is approaches k as x approaches infinity. Okay, let me understand what they're saying. Asymptotically stable solution if c within this range approaches k as x approaches infinity. I see. If you choose this tiny range, then as x goes to infinity, no, I don't think that would work. I think if you choose a very small range, then as x goes to infinity, it will approach k. Y is equal to k is an asymptotically unstable solution to the differential equation if there exists an epsilon more than 0 such that for any value c within this range, the solution to the initial value problem never approaches k as x approaches infinity. Okay. I think let's take this. As x goes to infinity, this will go higher, I'm assuming. Y is equal to k is an asymptotically semi-solution to the differential equation if it is neither asymptotically stable nor unstable. What do they mean by this word asymptotically? Um, Now we return to the differential equation with the initial condition y0 is equal to 0.5. The direction field for this initial value problem along with the corresponding solution is shown here. Okay, the values of the solution to this initial value problem stay between y is equal to -2 and y is equal to 2. Which are equilibrium solutions to the differential equation. However, an initial value problem starting with y between -2 and 2 never cross the equilibrium solution y is equal to 2 and y is equal to -2. Therefore, since y square minus 4 is less than 0 for x is greater than 3, y is decreasing and therefore approaching -2. Therefore, y is equal to -2 is an asymptotically stable solution to the differential equation. What happens when the initial value is below? Wait, hold on. So if the line is between -2 and 2, it's never going to cross this barrier, right? This it's never going to cross y is equal to -2 and y is equal to 2. So when x approaches infinity, since y square minus 4 is less than 0 for x greater than 3. X greater than 3. What happens when the initial value is below y is equal to -2? With the scenario is illustrated in figure 4.11 with the initial value uh, y0 is equal to -3. We can see that for initial values y less than -2, for x is greater than 3, the derivative is more than 0. Okay, so if y is equal to -2 for x greater than 3, I think this is 3 over here with the lines are horizontal. So for x greater than 3, the derivative is more than 0. It's a positive. And y is increasing, therefore approaching -2. This reaffirms that y is equal to -2 is an asymptotically stable solution to the differential equation. Create a direction field. How do I create a direction field? Uh, okay, anyways, and identify any equilibrium solution. Equilibrium solution is where the derivative is 0, right? The difficulty suddenly increased by a large margin. Uh, Square y square plus y -2. So if this is 0, that means y is 3, because then this will be 0, or this part is 0. Y is equal to minus b slagging plus minus b square minus 4 times it by ac. 4 times 2 is 8 over 2a plus minus, this will become 9 3 2, which is then -1 plus 3 is 2 minus 1 minus 3 is negative 4. So either y is 3, 1 or negative 2. 1, 3, negative 2. So it's 1. That makes sense. If it's negative 2, that makes sense. Okay. Classify each of the equilibrium solutions as stable, unstable, or semi-stable. The derivative is constantly 0 at 1, 3, or negative 2, right? So the derivative is 0 over here. Uh, 0 over here. Zero at 3. 3, 1, negative 2. So now what? So the arrows are going horizontal, either this way or this way. It doesn't matter. We always display the arrow going right, right? Because we are displaying an increase in x. So between minus 2 and 2. So if y is less than 3, between 3 and 1, 1 square plus 1 minus 2. Oh, it is 1.75 square. Let's see, if I do uh, between 1 and 3, this is always positive. Between 1 and 3, this is always positive. 1 and 3. 1, 3 implies the derivative is always positive. Between 1 and negative 2, this part is positive. What about this part? Between 1 and negative 2. It's always negative, right? So the derivative is going downwards. Here the derivative is going upwards. If it's above 3, then also the derivative is more than 0, because both of them will be positive. It's below negative 2. And the derivative will still be positive, because this is going to be positive and this is going to be positive. As you can see here, the graph is positive. Now, oops. Now what? More than 0. More than 0. If it's, then it's more than 0. Okay. Between 1 and 3, more than 0. And between -2 and 1, less than 0. So it's going like this, I think. Like this, and like this. Now I don't know what to do after this. Let's see. 3, 1, -2, up, up, down, up. So up, up, down, up. But how do you know? What do you mean by stable, unstable, or semi-stable? Classify each of the equilibrium solutions as stable, unstable, or semi-stable. It's stable. Approaches k as x approaches infinity. So approaches k as x approaches infinity. Unstable if it never approaches k as x approaches infinity. Is this unstable? You can see that for initial value y is less than -2 and for x is greater than 3 y is increasing, and therefore of this is stable. Or from here onwards, it will approach the approach k as x approaches infinity, so it's stable. What about uh, below and -2? Oh, it's stable as x approaches infinity, right? What about the previous one? It doesn't talk about y is equal to 2. Therefore, all initial conditions close to y is equal to -2 approach y is equal to -2 and the solution is stable. For the solution y is equal to 1, all initial conditions above and below are repelled, pushed away from y is equal to 1. So this solution is unstable. Okay, now I understand. If the close values are approaching that, if the values close to k are approaching k when x is increasing, then the solution is stable. This so stable, unstable, and stable if it's from below, semi-stable, I guess. The solution y is equal to 3 is semi-stable because the initial condition is slightly greater than 3. The solution approaches infinity, and for initial condition slightly less than 3, the solution approaches y is equal to 3. Okay, now I understand. Okay, wait, hold on. I might have to go somewhere. And let me just check. How long is this? Euler's method. Uh, okay, let me read Euler's method and then I will end this frame. Consider the initial value problem. Derivative of y is equal to 2x minus 3. And the y0 is equal to 3. So, okay. Okay, so we are choosing this line. Integrating both sides of the differential equation gives us y is equal to x squared minus 3x plus c. For solving, c yields the particular solution. For the particular solution, y is equal to x squared minus 3x plus 3. The red graph consists of line segments that approximate the solution to the initial value problem. The graph starts at the same initial value 0, 3. Then the slope of the solution at any point is determined by the right-hand side of the differential equation, and the length of the line segment is determined by increasing x by the value 0.5 each time, and that's called the time step. This approach is the basis of Euler's method. Okay, so you're finding the approximation of the slope at that particular point. The idea behind direction fields, before we state Euler's method as a theorem, let's consider another initial value problem. Derivative of y is x squared minus y squared, and y when y of negative 1 is 2. The idea behind direction fields can also be applied to this problem to study the behavior of its solution. For example, at the point minus 2, 2, the slope of the solution is given by derivative of y minus derivative of y is equal to minus 3. So the slope of this tangent line to the solution at that point is also equal to negative 3. Now we define x naught is negative 1 and y naught is 2. Since the slope of the solution at this point is equal to negative 3, we can use the method of linear approximation to approximate y near negative 1 and 2. Okay, now we choose a step size. So this becomes a linear approximation. Now we choose a step size. The step size has a small value, typically 0.1. That serves as an increment for x. It is represented by the variable h. In an example, let h equals to 0.1. Incrementing x naught by h gives our next x value. x1 is minus 0.9. We can substitute minus 0.9 into the line approximation to calculate y1. We can then repeat the process to calculate x2 and y2. And then x2 is minus 0.8. This is the linear approximation, and y2 is y2 is 1.492. What we have just shown is the idea behind Euler's method. Repeating these steps gives a list of values for the solution. Okay, I think I understand now. But the step size is smaller, the approximation is better. For the linear approximation, we are using the derivative, but if the derivative is not known, we use the linear approximation, right? So let's say in that exercise, derivative of y is 3x squared derivative at 0 is equal to 1, because this would be 0. No. X would be 0. Then I'm getting confused. Uh, x0 is equal to 0, y0 is equal to now x0 is 0, y0 is 2 because of this. And is equal to -3. So 0, 2, and this is the gradient. 0, 2, and the gradient is here, -3. Now h is what? 0.1. So the next one, 0.1, y1 is equal to 2 plus uh, and then the derivative is 0.1, 0.1. How do you do the linear approximation? Mm, this is 1, right? I mean, this is 0.1 times. I'll just look at the answer. 002. It, yeah, n is 002, 0.1. I don't get that. Oh, this is the derivative, yeah. So using the previous derivative. Hold on. I don't know why I'm getting confused. So -3. You're using this derivative to find the value of 0.1. So -3 is equal to 3, 0.1 squared minus uh, plus 1. minus 2 minus 3. Since this is minus, all of this will become plus, and square root. But then how do you find the next one? Is this correct? 1.425? No, it is not correct. It is 1.7. So the actual derivative is this. And you're treating x as 0. Actual derivative with x naught and y naught is minus 3. Hold on, this is wrong. Minus 3. So minus 3. Minus 3. Y1. Sorry, I mean y0. And then this would be 1.7. And then the next step would be x2, which is 0.2. y2 is equal to y1 plus it with 0.1. Now I need to find f of x1 and y1. So x1 is 0.1, then y1 is 1.7. I have a calculator with me. Squared plus 1 minus, is that even correct? Minus 1.8, no wait, minus 1.86. The thing is, um, let me times it by 0.1. Yeah, actually, I think it's correct. I think I'll continue this tomorrow. We'll end the stream here. I need some more practice with this. Okay, I will end the stream here and then I guess I'll see you guys next time.